Welcome back, my dear students. In the previous lecture, we have discussed about the properties, some important properties of orthonormal sets or sequence. And we have established that every x, if you are given with an orthonormal set, every element x can be written as summation j is equal to 1 to n inner product x ej, and also we have established that summation j is equal to 1 to infinity modulus of inner product xej the whole square is less than or equal to norm x square. Here the coefficients inner product xej's are generally called Fourier coefficients. This, if you are given with an orthonormal set, this inner product xek are called Fourier coefficients. So there are a lot of applications for this as well. Now, Gram-Schmidt process of orthonormalization deals with constructing a class of orthonormal sets from a given linearly independent set. So the process is, if you are given with a linearly independent set consisting of finitely or infinitely many elements, using that set we can construct a new set or sequence of orthonormal sets, which means pairwise orthogonal and has a norm 1. So the process is as follows. So we are given with a set or a sequence xj, and we are constructing an orthonormal sequence ej, and also it should satisfy span e1 e2 etc en should be equal to span x1 x2 etc xn. This is our objective. So the process is, first take an element e1. So e1 is constructed by x1 by norm x1 is e1, where x1 is a non-zero element, and clearly e1 is not equal to 0, and norm e1 is equal to norm x1 by norm x1, which should be equal to 1. So norm e1 should be equal to 1, and also e1 is a multiple of x1, so clearly span e1 should be equal to span x1. Now using this we are constructing e2. So e1 satisfies our condition, that is step 2. Now we construct another element v2, which is defined as x2 minus inner product x2 e1 minus times e1. This is the general form of the expression, which is also non-zero vector. Okay, and because x1 x2 are linearly independent, and also inner product v2 e1, which means both of them are orthogonal, we are going to prove this, is equal to inner product x2 minus x2 e1 times e1 comma e1. Using the basic properties of inner product, this is inner product x2 e1 minus inner product of x2 e1 comma of e1 comma e1. This should be equal to inner product x2 e1 minus, if we can take the constant outside, inner product x2 e1 times inner product e1 e1. Now inner product e1 e1 is norm e1 square, which is already, which we have defined is for to be 1. This is inner product x2 e1 minus inner product x2 e1 should be equal to 0. So v2 is actually orthogonal to e1. And also we can choose e2 to be defined as v2 divided by norm v2. This is actually e2. Now span of e1 e2 e1 e2 should be equal to span of x1 x2, because e1 and e2 are linear combinations of x1 and x2. Now we have to prove that e1 e2 are actually orthogonal. So here also norm e2 should be equal to norm v2 by norm v2, which is actually equal to 1. So norm of e2 is 1. Now we have to prove that e2 and e1 are orthogonal. So inner product e1 e2 should be equal to inner product e1 times 1 by norm v1 v2 times v2. Now this is a real number, we can take it outside, its conjugate is the same, 1 by norm v2 times inner product e1 v2. Now we have already proved that inner product of e1 v2 or v2 e1 is equal to 0. e1 is orthogonal to v2. So this should be equal to 0. So e1 and e2 are orthogonal. So from x1 and x2 we constructed two elements e1 and e2. Both of them are pairwise orthogonal. Each of them has norm 1. Step 3. Now similarly we can construct v3, which is defined as x3 minus inner product x3 e1 times e1 minus x3 e2 times e2, which is clearly a non-zero vector because e1 and e2 are linear combinations of x1 and x2, and x1 x2 x3 are linearly independent. So their combination, one of them or two of them could not be right as the linear combination of the other two. So this is a linear combination, so which means it should not be equal to 0. And also we define E3 should be equal to V3 divided by norm V3. And now we will prove that V3 is orthogonal to E1 and V3 is orthogonal to E2. So inner product V3 E1 should be equal to inner product of x3 minus inner product x3 e1 times e1 minus x3 e2 times e2 comma e1, which should be equal to, by definition, inner product x3 e1 minus inner product x3 e1 times e1 comma e1 minus inner product x3 e2 inner product of e2 times e1, which is inner product x3 e1 minus, we take inner product x3 e1 outside times inner product e1 e1 minus, we take inner product x3 e2 outside. This is inner product e2 e1. Now e1 and e2 are orthogonal, so this part goes to 0. Norm of e1 is equal to 1, so this of inner product e1 e1 is 1. So this should be equal to inner product x3 e1 minus inner product x3 E1. So which should be equal to 0. So V3 is actually orthogonal to E1. Similarly, V3 is orthogonal to E2 as well. So inner product V3 E2 is equal to inner product x3 minus inner product x3 E1 times E1 minus x3 E2 times E2 comma E2, which should be equal to inner product x3 E2 minus inner product of x3 E1 of E1 times E comma E2 minus inner product x3 E2 times E2 comma E2, which should be equal to inner product x3 E2 minus, taking constant outside, inner product x3 E2 minus inner product E1 E2 minus inner product x3 E2 times inner product E2 E2. Now this is inner product E1 E2 is equal to 0, so this part goes to 0. Now inner product E2 E2 is actually 1, so this is inner product x3 E2 minus inner product x3 E2, which is actually 0. So V3 is actually orthogonal to E2 as well. So V3 is orthogonal to E2. Now using V3 we can define E3, which is defined as V3 divided by norm V3. And also norm E3 should be equal to norm V3 divided by norm V3, which is equal to 1. And also E3 is orthogonal to E1 because inner product E1 E3 should be equal to inner product E1 times 1 by norm V2 or V3 times V3, which is 1 by norm V3 times inner product E1 V3, which we have already proved that it is equal to 0. And E3 is orthogonal to E2 as well, since inner product E2 E3 should be equal to inner product E2 times 1 by norm V3 times V3, which should be equal to 1 by norm V3 times inner product E2 V3. Inner product E2 V3 is equal to 0. So E2 is orthogonal to E2 as well. So we have constructed three vectors E1, E2, E3 from x1, x2, x3. Each of them has norm 1 and each of them are pairwise orthogonal. So if you continue like this, at the nth stage we can construct like this. So in general we can construct Vn as xn minus summation k is equal to 1 to n to n minus 1 inner product xn ek times ek. And using this we can construct En as Vn divided by norm Vn, and norm of En should be equal to 1, and also Vn is orthogonal to E1, E2, etc. En minus 1. So from this we can easily say that En is orthogonal to E1, E2, etc. En minus 1. this can be easily established. So thus we can construct a class of orthonormal sequence from a given set of linearly independent vectors. I think I'll give this in general expression Vn is orthogonal to some Ej. I will prove that. So for that, inner product Vn Ej, where j is in between 1, 2, 3, etc. n minus 1, is actually xn minus summation k is equal to 1 to n minus 1, the product xn ek times ek comma ej, which by definition is equal to inner product xn ej minus, now we can take this outside, so summation k is equal to 1 to n minus 1 inner product xn ek times inner product ek ej. Now this inner product ek ej by previous construction are orthogonal, pairwise orthogonal, and all has norm 1. So when k not equal to j, this inner product ek ej is equal to 0. When k is equal to j, this becomes inner product ej ej, which is 1. So the corresponding term becomes inner product xn ej. All other terms becomes 0. So this should be equal to inner product xn ej minus inner product xn ej, because from when k not equal to j, this inner product ek ej becomes 0 and the corresponding term in general becomes 0. When k is equal to j, this term becomes 1. The only other corresponding term will be inner product xn ej. So difference between same terms which should be equal to 0. So Vn is orthogonal to ej for all j varies from 1, 2, 3, etc. n minus 1. Now using this we can assume that in general En is orthogonal to Ej, because inner product En Ej is equal to inner product En is actually, we can write Vn divided by norm Vn. We can write as such, divided by norm Vn comma Ej. This is 1 by norm Vn times Vn Ej. We have already proved that Vn is perpendicular to Ej for all j. So which means that inner product Vn Ej should be equal to 0. So that part becomes 0. That is En is orthogonal to Ej for all j varies from 1 to 3 etc. n minus 1. And also norm En is equal to norm Vn divided by norm Vn, which is actually 1. Thus we have constructed from x1, x2 etc. xn, which is the linearly independent set, we have constructed a sequence e1 or a set e1 e2 etc. en, which is orthonormal. So this process is called Gram-Schmidt process of orthonormalization. So from any given set or sequence of linearly independent collection of elements, we can construct an orthonormal class of sets or sequence. This is the idea. Thank you.